One of my students, Janen's, handing out a souvenir. It's a honey straw to help you remember this lecture and think about it. And so I'm Professor Tim Denison. I am in the biomedical engineering panel and the electrical panel, and I do beekeeping as a hobby and help support the students. There's actually a student beekeeping society here. And I'm going to kind of merge it a bit together today and give you kind of a general principle of how coming to Oxford and learning general engineering science principles, you can apply it both on your job and in your hobby. It's actually a way of thinking about the world, and that's my kind of takeaway today. So let's start out, system engineering is important. So what is system engineering? Really interdisciplinary approach to designing, integrating, managing complex systems through their life cycle. Really ensuring that all of the elements are put together in a good place. And the simple way is, it's a way of bringing everything together in a complex project and having it smoothly work for whoever your intended customer is. And so when I'm at Oxford, when I'm in this building with my students, we work on brain implants and some other neurotechnology. So Dan Rogers is a collaborator. He's going to talk about external systems that we work on together. But this is an example of an implant. This is a CT image from a skull. And the top, that's a little computer we basically designed the circuits for. And then electrodes are placed by my Oxford neurosurgeon partner, Alex Green, in different parts of the brain. And we currently have trials active in treating pediatric epilepsy down at Great Ormond Street in London with Martin Tisdale. And then with Alex, chronic pain and some work in Parkinson's disease. And so students do get access, even as undergraduates. They're helping me to refine the system, especially the components that many of the children rely on for recharging. So as you can imagine, you just don't show up and say, here's a brain implant, let's put it in. There's a lot of considerations that you need to have. And those, when I teach the class, we go through this systematically. But on the right-hand side, we think about the function of the device. So is there an unmet clinical need? Like, are we solving a real problem that's important? Is the science there? Is it a plausible way that we're interfacing with the brain? And is the technology mature? These are going into human participants, volunteers, for basically the rest of their lives. And so we have to make sure that what we're building is actually going to be robust. At the same side, and you actually get exposed to this at Oxford, there's the pragmatic elements of what I kind of lump as healthcare economics. The regulatory pathway, working with the government to get approval for your study, and the ethics, making sure the workflow is there. Many of you are spoiled. You also grew up with consumer electronics and the like. When we're treating people, say, maybe in their 80s, they're not as familiar with technology. So are they going to be able to operate the system? And then the economics, especially in England, we have the National Health Service. We're very focused on making sure that we provide quality of life years at an acceptable cost. Anybody have a sense of the value of your life right now on the NHS? You young people? It's about £25,000. So for every year I can give you a perfect life, I can charge £25,000. And so that's a design problem. So that's the kind of thing we think about, day in, day out when we're building these systems. Now for today, I'm going to break it down into kind of 4 steps. And if you think about interfaces, so interfaces such as the door, how do we manage energy, how do we manage information, and how do we manage risk? These are kind of 4 topics when I give you a problem. You can break it down systematically. So go home and any problem that you face, you're given a chore by one of your parents, you can think about, is this chore? What elements are important for me to solve? So when I wrap up this lecture and go home tomorrow, I'm going to work on my beehives and get ready for the winter. So I'm going to kind of walk you through, what do I think about applying these techniques and managing the beehives? So first, let's think about interfaces. So has anyone seen a beehive out in the wild? Yeah. So what's going on inside of there is we're actually trying to recreate the environment that the bees have in basically a tree, their natural environment. So there's an area where the brood grows, where the next generation of bees are being raised by the queen and the workers who are supporting them. At the top are the honey stores. Over here are the drones. Those are the boy bees, the male bees. Very small portion of the beehive. It's really power to the women. They run the hive. And the boys have one role, which is to mate with the queen for the next generation of bees. So we're trying to replicate that in the design of our interfaces, but we're very discrete. So the large box at the bottom are where the eggs are laid and the next generation grows. There's a queen excluder, so that actually prevents the queen from going up because of her size. And then we have the honey supers on top. So this is where we gather the honey. Now the reason we exclude the queen is we want to keep the honey very pure for the purpose of harvesting it. Now one thing to also emphasize is it's a very modular design. So we can stack boxes on and up, and that actually is so we can take boxes off for the winter so the bees don't have to keep a big space warm. But then as they're rapidly growing up honey in the spring, we can keep stacking boxes on top of one after the other. Now one thing that's interesting in the hive, notice this very regular space, very regular spacing. And that's not random. So the first person who was actually kind of exploring with the design of a beehive would notice in nature, bees have this very fine spacing. It's called the bee space. And if you make the dimensions of your hive just right for the bee space, you can have a very ordered system. So it's very modular. We can pull frames in and out. It's not chaos. So actually the design of the box and all the dimensions are very carefully controlled. So what goes wrong if you don't do that? So this is where we kind of just left the top of the hive. We didn't create the proper space. And just like any of us, we go back to our nature. The bees create what they call wild comb. So they say, well, this is an open space. I'm going to build my comb, but there's no structure to it. And so this becomes very hard for us to manage. And so I like to tease my apiary manager because he sounds just like a Norbot from Wallace and Gromit. He's always going around neat and tidy, neat and tidy. And so one of the key goals is to manage the hive by keeping it very structured and obeying the natural bee space. And it's kind of that management of an interface for the bees. So energy, you all have a little bit of bee energy, sitting on that straw. And just think about this, for every teaspoon of honey, that's 12 bees' life. So 12 bees, their entire life went into making that teaspoon of honey. And so what is the key for the energy? It's resource management. They have a very tough job. So this is a plot of the year going by. So I don't expect you to read it. The big one because it's too small font. It's basically the key point is the green and the blue over the year. So January through December. Nectar flows in Oxford kind of between March and maybe mid-July, late July. We're at the very tail end now with ivy. Doesn't make great nectar for the bees. So they have to gather all of their food for the year in this very short window. And so their population, they're actually now the green, they're on the decaying curve. So this is October right now. And the reason for that is they're getting rid of their resources. They're actually shrinking their population of the hive down so that they can actually manage to get themselves through the winter. But then the challenge is, when the winter solstice comes, they have to start to go at risk and build the hive back up, because it takes about 1 month for a new generation of bees to come, and they have to grow up. And just like you as a family, you just don't necessarily go one generation from 2 parents to this entire class size in order to support the harvest. So they have to go through a few generations to build up. So it's a real challenge for the bees to manage all of this. So we can think about this as a dynamic system. Oh, there we go. That's all right. Happens to me too sometimes. So it's a dynamic system, so we can model this and think about it. But the critical element is the honey cell. And so we're sitting on those supers. We want to get some honey eventually. And the bees need it for the winter. And so we can write dynamic equations. And basically, we look at these flows. So we've got pollen coming in. That's their protein. So just like you, the bees need protein. The nectar is their sugar water, their carbohydrates. And they just need water as well. And we see how that flows to the hive. So when in the spring, when we get these nectar flows, there's an excess of nectar coming in, and as long as that's greater than what's required for the foragers and the nurse bees, that gets stored away for the winter. So we can build, they need that excess to build up, and then when they hit the winter time, they're going to draw down on that energy storage, the honey cells. And so one way you can deal with that is you need to store up a lot of honey, and the other thing is you get rid of the population. So especially for those of you who are sisters with a brother, you'll appreciate this. The first thing the bees do is when the nectar goes away, they chuck all of the drones, all the boys out of the hive. Just kind of they're just excluded. They're all thrown out. That's the first way they start to manage their resources, to get rid of all the males in the hive, because they are providing no useful work. So now the one thing that I've neglected is in this flow diagram is, of course, the beekeeper. And so I'm an unplanned for, I'm basically a bear, showing up and robbing their hive of its winter resources. And so I have to think about this as I'm mucking up their dynamic system. So one of the roles of a beekeeper is I have a kind of an agreement with the beehive, well, maybe a one-way agreement, but to honor them, I take some of their honey, so I can give it to you, put it on my toast, but then I make sure, one, that they have enough energy either with excess honey in the hive, or we'll go in with baker's fondant throughout the winter and I'll feed them. So just like the fondant you'll get at the bakery, we'll put that on top of the hive to make sure that they have the resources they need for the year. So what did they, are they sitting there just, eating like you, watching Netflix, just chewing away? What's the real reason they need this energy? And it's about the order of 50 watts. So in the beehive, they're constantly generating 50 watts. It's to stay warm. So you may have noticed on that first screen I showed of the interfaces, that was from my beehive, and there was a circle. That was actually on the winter solstice where I opened it up to treat them. And they form in the winter this ball. So for those of you students that you learn about thermodynamics in your second year here. So the bees actually cluster into a sphere because it's very efficient. They then create a mantle around themselves, the outer bee shell. And then inside, they're actually eating their honey, but they can disconnect their wings, kind of flex their muscles. And so they're sitting there actually pretending like they're flying, but their wings aren't moving, but they're generating heat. And they'll actually keep themselves in the 20 degrees Celsius, 30 degrees Celsius. And then when they start to grow up, the next generation, it actually goes up to basically 35 Celsius. So when you're out walking and you see a beehive in February, and say it's 5 degrees Celsius, inside of the hive, it's actually a very balmy, kind of mid-30s. But that's generating, they're basically taking the heat, flexing their muscles, and keeping themselves warm. So bees have fascinated people for quite a long time because they manage information. They're very unique. Other than humans, maybe a few like dolphins and the like, but in the insect world, they're unique because they can convey information to each other. And so Carl von Frisch won the Nobel Prize for this by understanding the waggle dance. Have you guys who's heard of the waggle dance from bees? Yeah, it's a few people. So what make bees so powerful in the insect world, and actually put other bees, frankly, at risk, other pollinators at risk, is they coordinate. So it's just like you as undergraduates. I'm going to have a lecture. I'm going to have excess food left over. One of you is going to go explore, and you're going to walk by my table after my lecture hall and say, oh, there's a bunch of sandwiches left. You're going to go back to your college hall, go to your flatmates and say, sandwiches. Here's the lecture hall. These are coordinates. Or you're going to get on WhatsApp. Here's the lecture hall coordinates. So the way the bees do that is they come back, they're kind of spread out. When one of them finds a great source, they come back into the hive. They use gravity. So remember, there's no lights on in the hive. So it's kind of, they're using gravity and vibrations to communicate. So straight up is where the sun is pointing. So one way I can give you a coordinate is straight up is where the sun is right now. Then you do the angle compared to straight up, and that's the angle for where the flower is. You do your dance in that direction, and the length that I do the dance is an approximation for how far it is. So I could do the same with you. I could actually like say this way is up, that's where the sun is right now, dance in that direction, and then you basically say, oh, that was 3 seconds, okay, that's about 1.5 miles, and you'll walk outside, there's the sun, there's the rough angle, here's my approximation. So Frisch figured this out, von Frisch won the Nobel Prize for it, and that's why bees are actually so powerful as pollinators. There's a whole side of the ethics of beekeeping, which is also worth debate, because they're actually incredibly good pollinators. They're putting other pollinators at risk. And that's one of the classes we study here, is the ethics of engineering. Like when you're building brain implants, when you're building bridges, what are our responsibilities as engineers and some of our unintended consequences? So the other thing that bees are masters of is operations. So those of you in engineering who want to get into operations for like manufacturing plants and the like, they have a problem where, okay, they've sent out all these bees, they're gathering nectar, they bring it back to the hive, how do they get it stored? So there's another side of this where they basically transport it the entrance of the hive, and then they go and store those away in cells or feed other workers. So you got two dynamic systems trying to work together, and you've got to balance these out. And so bees have been masterful at finding the balance. And so we talked about the waggle dance, and so it's based on the time. So a bee comes back into the hive. If it very quickly transfers the food, it says, all right, there's plenty of people available to gather and to store the honey, so let me do my waggle dance and recruit more people. But then if it takes a long time to find someone to hand the nectar off to, they start to take another action. And this is discovered by Tom Seeley. Then they start what is called the tremble dance. It's a different kind of dance, and that's to recruit more people to actually be storing. So you think, if I take the class, I start sending you out, and you find a really rich, set of free sandwiches left over at lecture hall, and you're bringing it back for us to store. If you can't find someone to hand the sandwich to, we're going to recruit more sandwich storers. And so that's what the bees are doing with this other dance. But the last part is you need negative feedback. So pretty much in any control system, and we talked about that earlier, you learn about controls as well, and thinking about control problems. Negative feedback helps you to stabilize the system. So the last bit of negative feedback is when the storage time gets too big, the bees start bumping into each other. So if you start to do a waggle dance and say, I found some food, other bees will come in and basically say, stop it. Stop it. Stop trying to recruit people because we can't support it. And so these very rich control systems problems that are flowing and being studied in the hive. And you can actually break this down as an engineer and really start to understand it. Now, the pragmatic thing is, in terms of information flow, is that bees communicate with pheromones. And so we use smoke. And so smoke actually does two things, at least two things. One, it helps to mask the pheromones. So they say, hey, that big guy with the beard is breaking into the hive again. They find that mildly annoying. You can imagine someone showed up in your house every Saturday and took the roof off, looked at all your marked homework and said, okay, taking that, I'm going to take some of your projects. They get defensive. But the other thing it does is the smoke that kicks off a response, and they go and start eating honey because they're actually feeling a threat. And so they're saying, we may have to evacuate, so let's actually tank up. So it's kind of like if I say, okay, wake you up at 2 a.m. as your college tutor, we're going out on an all-night hike. First thing you'll do is probably down a few energy bars, get ready for the hike. So when they fill their abdomens, it actually makes it harder for them to sting you because their tummies are full. So it's harder for them to build. So if you get to block the pheromones, it also makes it a little bit harder for them to sting you. So the last thing is risk management. So in engineering, it's really important. We think about our designs, but we also have to think about risk. What are we doing to protect our customers from our design going wrong? And so this little blue dot, that marks Beatrice. So she's in my second hive. And hives are at risk because if you lose the queen, there's one queen that's responsible for all of those workers and drones. So she's the mother in this peak of spring of 60,000 workers in the hive. So moms, that's an accomplishment. So, but if you lose that mom, that's it. And so the bees have adapted in their cycles where they have one queen usually at any time. There's one queen in a hive. And then they're growing the drones and the workers. And this is their life cycle. Time's going by in days. But bees have adapted a redundancy system where in this period between 3 and 6 days, they can actually feed what's called the royal jelly. And a worker will be converted over into their next queen. And so that's kind of a backup system for them. But now what happens, this is where beekeepers come in, if the bees miss that opportunity, what we can do is go and grab a set of, basically a frame from another hive that has those workers available, and we'll put it into the hive that needs a queen. And then the workers will do the job of growing up their next queen. So that's one example of risk management, of kind of, we always keep our eye on the queen, make sure she's healthy, as do the workers, and then have this backup plan in case we need to replace her. So let's come back to brain implants, thinking about the work we're doing at Oxford. So of course here's our system. What are the things we think about? Interfaces. So of course, how do we get this device to sit snugly in the cranium? How do we create materials that can contact the brain and are safe, don't actually cause damage to the tissue? These are the kind of material science problems and interface challenges we have, including helping the surgeons make sure they get the device in the right place. Energy management. Just like you charge, say, your cell phone, there's a battery inside of this device, and so we spend a lot of time designing headphones and other systems so that our patients can very easily charge up their device. And in the case at Great Ormond Street, we're going down to children who are age 5 with some severe challenges, and so we spend a lot of time thinking about how we can make an acceptable recharge system for them. Then the information. So we're actually, with the electrodes, we're putting patterns of stimulation into the brain, modulating the brain rhythms to try to restore them to a more healthy state. And one of the active projects right now, actually, literally, my students are up the hill as we speak at the John Radcliffe Hospital with the clinicians, trying out a new system that actually measures brain signals and uses that to adapt the stimulation. And then in risk, I'm just flashing this up. Yannen's been through my class. We have very systematic ways to think about engineering designs and how they can go wrong. So just, you read about automated systems, like I talked about this automaticity, self-driving cars, are a key example right now of how do you create these automated systems but that they're safe, especially if something should go wrong, and thinking very systematically about that. So I know we confused you a little bit today. My change of my title didn't make it onto the overhead or maybe on the web, but the outcome of all of this work in terms of system engineering does show up in a project. This was on the BBC last summer. So this is a young man, Oren, who has Lennox-Gastaut epilepsy, and he was our lead pilot, and they followed his story, and they'll be doing a follow-up. But if you're interested in that specific epilepsy case, that's actually on YouTube, is another open day lecture that I do. I talk about the design of brain implants, but also technology for Harare, Zimbabwe, and kind of the similarities and differences of treating epilepsy there. So this was a little experiment. What I wanted to do is kind of give you a portrait of things that go from my hobby of beekeeping down into the way we think about brain implants. And my key point is that coming in and getting a general engineering science degree, I think really sets you up well for thinking systematically about very complex problems. And that's an advantage of coming and working with us and learning. So thank you for your time, and I can take a few questions, I think.